Okay, welcome to the class, and as the title says, we are going to start a new topic. Okay, for those of you who are not comfortable or you have not heard about this acronym, this is MIMO. This is called multiple input, multiple output. Okay, and which essentially means input means multiple antennas at the transmitter, because the transmitter is the input wherein the input data is being fed. Output is the receiver, okay, wherein the receiver data is coming out. Okay, so it is multiple input, multiple output. These multiple stand for multiple transmit and receive antennas. Okay, so we'll only touch these basic concepts which are relevant for 5G NR. I teach a full semester course on MIMO. Okay, we'll cover this in 1 or 1.5 class. Okay, right. So, and we'll only see what is relevant, and that will help us in introducing the concept of these different reference signals. Okay, and they are defined especially for MIMO. Okay, you see this, there are 3 different reference signals. Reference signal is basically they are pilots. Okay, sounding reference signal, channel state information reference signal, demodulation reference signal. We are going to see all of them. Okay, and they make sense when we start talking about MIMO. Okay, so what are we saying? We'll learn about MIMO and we'll motivate the use of these pilot signals, and why 3 different kind of pilot signals. Okay, so let's start. This is our favorite beast, phi is equal to x plus n. Okay, what is this? This is, we have seen that capacity in the beginning of this course. This is log 1 plus SNR. Okay, capacity, spectral efficiency. Okay, what is this P by N naught? P by N naught is SNR. Okay, now how does logarithm behave? Okay, we did not talk about this earlier. Okay, logarithm, if P by N naught is much less than 1. Okay, what are we saying here? P by N naught, SNR is, its value is much less than 1. Okay, P by N naught is a ratio. Okay, it can be greater than 1, it can be less than 1, and it cannot be less than 0. Okay, the power, when it's a ratio of 2 powers. So what are we saying here? So we call this as a low SNR regime. Okay, right? When this is happening, that's, so in that case, the logarithm is approximately equal to this. That's what, this is basic logarithm behavior, nothing to do with MIMO, nothing to do with wireless. Okay, if x is a number, if P by naught, N naught is a number which is much less than 1, they are same. Okay, right? So what is this telling us? If we are in a low SNR regime, okay, correct? If, and typically what will happen here is, low SNR means, let's say you are in a basement of a building. Okay, right? I'm taking an extreme example. Okay, now this spectral efficiency will become like this. Okay, what is happening? So if you look at this carefully, the capacity has become a linear function of SNR in low SNR regime, right? Okay, and if you increase the SNR by a factor of 2, your capacity will increase by a factor of 2. If you increase this SNR by a factor of 4, the capacity increases by a factor of 4. It is as simple as that. Okay, what is this logarithm, what is this behavior telling us? That if you are in low SNR regime, try to increase the SNR as much as possible. It will give you the linear increase. Factor of 10 increase in SNR will give you 10 times increase in the capacity. That's what it is telling, because you are in a low SNR regime, and if you increase the SNR, it's going to give you these kind of gains. Okay, right? Okay, capacity increases linearly with SNR. When it is in high SNR regime, what happens? What is this high SNR regime? What are we saying? P by N naught is much greater than 1. Okay, what happens? This is much greater than 1, 1 can be ignored. Correct? Again, logarithm behavior. So you get log of P by N naught. Now you see this, you increase P by N naught by a factor of 16, how much the capacity increases? It only increases by a factor of 4. See the difference? Because you are in a high SNR regime, increasing SNR gives you a diminishing returns. That's what it's saying, right? Okay, because you already have so much of SNR. Okay, so capacity increases only logarithmically with SNR, not very impressive, right? Okay, so, and we'll see this, I'm not going to touch upon this in this class. In this case, when the high SNR, okay, you don't really care about SNR. Okay, what you care in high SNR regime is, you basically, how can you transmit data in parallel. Okay, how can you increase the data rate in this regime? Basically transmitting data in parallel. Okay, so it might look like a little awkward that how can you transmit data in parallel, we will see all that. Okay, but what are we saying here? What am I here? That at least in low SNR regime, okay, if you can increase the SNR, okay, you get a linear increase in capacity. Very impressive, right? Okay, and the system is starved of SNR. You increase the SNR, your capacity increases linearly. Okay. Now, what are we saying? Okay, the transmit power, the power which is being transmitted, the noise, they are fixed. Noise, so what is the noise floor? Okay, which gets added at the receiver front end, that's fixed. You cannot do anything to both of them. Then how are you going to increase the SNR? That's the question we are asking. Correct? You look at this P by N naught, that's how we have defined. Okay, right? So multiple receive or transmit antenna can help us in increasing the SNR, and that's what I am going to show you. Okay, right? And so that's the key idea. The key idea here is when the system is in a low SNR regime, okay, you want to increase the SNR, P and N naught are fixed. How do you do that? Okay, so in the low SNR regime, if your transmitter has multiple transmit antenna, receiver has only single antenna, then also you can increase the SNR. Okay, but at high SNR regime, well, you should have both multiple antennas at the transmitter and multiple antennas at the receiver. Okay, then what you can do here is at the high SNR regime, you can transmit multiple symbols in parallel. What are we saying here? On the same PRB, just for example, okay, you can transmit data, 2 streams of data. You can transmit 2 transport blocks to make things easier for us to understand. Okay, right? As of now, what are we doing? On each PRB, we are transmitting only 1 transport block. Correct? If MIMO is there, what will help you? It will help you in transmitting on the same PRB 2 different transport blocks. I will show you how that happens. Okay, so in the same PRB, if we are transmitting 2 transport blocks, your data rate is getting doubled, right? Okay, and that typically happens in the high SNR regime, okay, where you don't care about the SNR because increasing SNR is giving you diminishing returns. Capacity is only increasing logarithmically, okay, right? If both these multiple transmit and receive antennas are there, capacity will increase linearly in terms of number of antennas. Okay, so you have 2 transmit and 2 receive antenna, capacity doubles theoretically. If you have 4 transmit and 4 receive antennas, it will become 4 times. Okay, right? So that is the idea. Okay, so in this class we'll look at this particular regime. Okay, how do you increase the SNR? Okay, so let's see that. So this is our single antenna system. We have. Okay, so what is this? This is the transmit symbol gets multiplied by h, y is equal to hx plus n. Where is this system model applicable? OFDM system, we have seen that, right? Okay, y is equal to hx plus n over each subcarrier, correct? Okay, this is a system model, that's why OFDM is used. Okay, so now if you look at this, what will be the SNR? Signal power is h square, x, if x has power p, SNR becomes p into h square by, if n has variance n naught, this becomes the SNR, right? So SC is, spectral efficiency is there for this, right? Okay, fine. So the SNR is this, channel has come. Okay, now let's see what are we doing here. Okay, there is only 1 transmit antenna. What am I doing here? Okay, I put 2 receive antennas. Fine. Okay, let's say this is your mobile base station. It has 2 receive antennas. Okay, correct. Now what will happen here? So what will be the signal received at first antenna? Y1 is equal to h1x plus n. That is the channel from first antenna to second antenna. From transmit antenna to first receive antenna is h1. We are calling that channel as h1. From transmit antenna to second receive antenna, we are calling that channel as h2. So what will be the signal received here? h2x plus n2. Signal received here will be y1, it will be h1x plus n1. So you have 2 copies of the signal in which x is contained. Both of them are noisy, n1 and n2 independent noise, and then h1 and h2 are also independent. Okay, different channels. Okay, you can, and I told you this, like consider this uplink transmission wherein mobile has single antenna and base station has 2 antennas. Okay, right. So what will this base station do? It has received these 2 signals. Okay, what it does is, okay, you see this, it weighs and adds these 2 signals. What is this weighing? Okay, just to, why does it need to weigh, and what is this weighing? That is what I am going to show you. Okay. What is it weighing it with? See, this is y1, it is weighing it with h1 star, it takes y2, it is weighing it with h2 star. Okay. This is called weighing and then adding these two signals. And why it is weighing these two signals? The reason is, let us say, just we take extreme cases, if h1 is 0, right, if the channel is so bad over here that you receive only noise, correct, and let us say h2 is 1, what will this antenna receive? X plus n2, right. So, how is it weighing? It is weighing, what will happen? h1 is 0, 0 into y1 plus h2 is 1, 1 into y2. Why does it need to weigh? It is giving importance to these signals while adding them. Weighing is the importance, okay, and how much it is importance is being given is in proportional to the channel it is observing. If the channel is bad, right, if h1 is low, it will get lower importance, if h1 is high, it will get higher importance. And the worst case was h1 is 0, right, okay, what is happening is giving 0 importance to it. So, it is weighing this signal according to it, the strength of the signal it has received, correct. And so, if the lower strength signal, lower importance, if the higher strength signal, higher importance, that is all, correct. We keep doing this in our daily life also. You know what to give importance to. If you have to add, if you have to hear the same information from two sources, one is noisy, other one is pure, okay, one is Facebook, other one are your parents, okay, right. Where are you going to? Facebook you will weigh it down, parents you will weigh them up if you are sensible, right, okay, fine. So, that is the information, right, that is how you weigh them. You do it in your daily life also, okay, right. So, that is what is happening over here, and I will show you, I will not give you the proof, but this is the best thing to be done, okay, fine. So, what is happening? You substitute y1 and y2 over here. We know what is y1, what is y2. I have just done that. y1 is h1x plus n1 and y2 is h2x plus n2. Why I am doing h1 star? Because h1 and h2 are complex. Okay. So, what will happen? Okay. So, h1, y1 is h1x. So, that will become h1 star into h1 will become mod h1 square into x plus h1 star into n1. This is the first signal. You see this, correct? Blue one is this. This is the first signal. I am just written them together. Second one is h2x, right? Okay. Now, let us calculate the SNR of this. What is the SNR? Power of this divided by the power of this, correct? What is the power of this? Square into p. Power of x is p, that is what I have written in the numerator. What is the power of noise? Square of this, right? Again, that this is what, so the power of this is, I keep writing this, but correct, okay. Now, you open this, the cross terms are going to go to 0 because noise is independent and with 0 mean, that is how we assume, right. So, what are you left with? These individual terms, that is what they are coming in the denominator, correct. There is no cross term, n1 n2 term is going to 0 because both of them are independent with 0 mean. So, you get this. Now, what happens? This gets cancelled, one of the power gets cancelled and this is the SNR, right, okay, fine. Now, let us say, so just for example, if h1 is 1, h2 is minus 0.5, what will be the SNR? Just substitute it over here, you will get 1.25 p by n naught, right, okay, fine. This is, I have just substituted these values. Now, let us say there is this is not there, correct, okay. What will be the SNR? If you look at this channel, 0.25 p by n naught, right, okay, and SNR is, let us say, is a poor SNR, 0.25 by p by n naught, okay. You are in the basement of a building. Suddenly, base station has the second antenna, right, this one. What happening? SNR gets increased by a factor of 5, right. The capacity increases by a factor of 5 because you are in a low SNR regime. That is how the second antenna is helping. If this was not there, you were in a bad state, right, okay. So, you see the gain 5 times increase with such a simple example, okay. That is what keeps happening, So that's why you use multiple antennas, okay, one big reason, okay, so that even if wherever you are, you can, base station is able to gets a reasonable SNR so that it can decode your signal, okay. I have not increased P, I have not increased N naught, I have not reduced N naught, I have not done anything, P by N naught remains same, right, okay. And why you are what are you doing? You are adding, you are making these channels, okay, you have one additional signal which you are receiving, which is much stronger than this signal. So you are getting this, okay, right, okay. So this is one case, we consider this as uplink, right. Now what is this? There are two receive antenna, there is one transmit antenna, correct. This is uplink, your mobile base station. What happens now, okay. So, okay, before we go there, so this is called the match filtering, okay, and this match filtering is the best operation to do. It maximizes the SNR. You cannot have a SNR greater than this. That is, you use basic Cauchy-Schwarz inequality, you can prove it. We are not going to do that, okay. This is the best operation you can do. Now this was for uplink. What happens in the downlink? Okay, so don't look at what I am doing here, okay. So what are we saying here? Counterpart of uplink, okay, the downlink, there are two transmit antenna and there is one receive antenna, fine. Because why are we considering this kind of system? Because typically you can install a lot of antennas at the base station and very few antennas at the mobile station. It is a small device, right, okay. So we are considering this example where there are now multiple transmit antennas and only one receive antenna, fine, okay. So, and this is downlink, this scenario mimics downlink transmission. Now first case we are considering, okay. So what are we saying here? The channel from this first transmit antenna to the receive antenna is H1, channel from second transmit antenna to the receive antenna is H2, okay, that is what we are saying. The first case, okay, here I will take two cases, okay. The first case what I am saying here is, these channels are not known at the transmitter, okay, right. Who knows, by the way, who knows that channel, okay, the receiver is receiving the signal, correct, okay. So it is easier for receiver to estimate the channel, because who has the received signal, where is this, what is happening here, let us even go back, I think that is important. So what is this, y1 is equal to h1 x plus n1, who is observing this channel? The receiver, okay, right. And later I will show you when these pilot signals come, it is like, what happens, I think, I do not remember whether we discussed in this class, if x is a pilot signal, let us say x is set to 1, okay, right. So what will happen, the signal received here will be y1 is equal to h1 plus n1, okay. What is happening, y1 is actually the channel, so receiver is able to estimate the channel, correct, okay. Fine, if data is not transmitted, some signal is transmitted, receiver is able to estimate the channel exactly, okay. Some noisy, y1 will be h1 plus n1, let us say n1 is also close to 0, okay, right. So y1 becomes h1, so it is the receiver which can easily estimate the channel, okay, right. It is very difficult for the transmitter to know the channel, because transmitter does not see the channel, it is the receiver which is seeing the channel. I just told you how, right, okay, fine. So the first case, assume that h1 and h2 are not known at the transmitter, okay, right. What happens in that case? So what is it going to do, okay. So two transmit antennas, okay, what has it done? It is transmit x by root 2 from each antenna. There is only one signal x, okay. What is it doing? You do not want to change the power, power should always be P. Even though you have two transmit antennas, you do not want to change the transmit power, because we said, right, P by N naught remains same, okay. And that is how typically it happens in real life, that you have as many antennas, right, okay, so you do not really want to increase the power, okay. So, and that is what we are doing, because the constraint is imposed on the total power. How do you distribute across antennas? That is another problem, and what we are doing here, we are distributing them equally across these two antennas, correct, okay. So transmit power of this is P by 2, transmit power of this is P by 2 if x has power P, so total power is P, okay. right. So, that is what is happening. Okay. Now, what happens? So, what will be the received signal? h1x by root 2 plus h2x by root 2, correct? What happens? h1 plus h2x by root 2 plus, what is the SNR in this case? Let us call that as h1 plus h2 as h tilde x by root 2. What will be the SNR? h tilde square p by 2 by n naught, correct? Power of this is h tilde square p by 2 by n naught is the noise power. Let us take this example again which we did for the last case, okay? And when there was one transmit antenna and two receive antenna, h1 was 1, h2 was minus 0.5. What is the SNR becomes? 1 minus 0.5, 0.25, h tilde is 0.25, right? So, SNR becomes 0.25 p by 2 n naught, 0.125 p by n naught. What was the SNR in the last case? When there were one transmit antenna and two receive antenna, 1.25 p by n naught, right? Now, at this stage it looks like that these two transmit antennas are not helping you much, because the power is actually 1.25, is 10 times lesser than the earlier case wherein we had one transmit antenna and two receive antennas, right? Fine. So, there is a big shock that what we are saying here, that transmit antennas, when this is not known at the transmitter, it performs badly when compared with multiple receive antennas case, okay? And this is the factor, okay? I will show you when this is known at the transmitter, you will exactly get 1.25 p by n naught. That is the next example, that is what I am going to show you. So, what am I telling you? If you know the channel at the transmitter, okay, having multiple transmit antennas or multiple receive antennas gives you exactly the same gain, okay. That is why this information, channel information, is crucial at the transmitter, okay. That is why UE keeps feeding back this information, so that base station can use that information in the downlink to do this, to weigh the transmit signals. That is what we are going to see, okay. So, 10 time reduction in SNR, can we do better? Yes, okay, and that is what I am going to show you. Assume h1 and h2 are known at the transmitter, okay, very important assumption. So, what is it going to do now, okay, right? So, here I should remove this little, okay, fine. So, what is it going to do? It is basically, instead of transmitting x by root 2, what is it doing? It is weighing the signal, again weighing, okay, weighing the signal by how much? h1 star, because the channel from here is h1. So, it is weighing the signal by h1 star, is dividing it by some constant root c. Why this constant root c? I will make it clear to you, okay. Similarly, what is it transmitting from second antenna? Is transmitting h2 star by x by root c, okay, right. I call this as x1 tilde, the whole of this, and the whole of this is x2 tilde, fine, okay, some notation, and this is called transmit precoding, okay. So, what will be the transmit power? Transmit power is h1 square p by c, right, x square is p, I have not put it over here, plus h2 square x square by c, roots is in the denominator, okay. So, what will be the total power? h1 square plus h2 square p by c. You do not want to change the transmit power, it should always be p, right. What will you set c as? This, right. So, c should be equal to h1 square plus h2 square, so that the transmit power does not get increased or reduced. That is why this c. So, I am making sure that transmit power is always p by setting this c accordingly, okay. Very simple example. So, what happens after that? So, what are we transmitting? So, okay, c is all. So, your transmit signal is designed from both antennas. You know what c should be, because h is known at the transmitter, correct, okay. So, what will you receive? h1 x1 tilde plus h2 x2 tilde plus noise. There is no different noise, because there is only one receive antenna. Noise gets added only at the receiver front end, it does not get added on air. Students have this doubt, why not n1 plus n2? There is only one receiver front end, only one noise, okay, right. So, that is what it is, okay. So, what it is? You have to basically calculate the SNR, okay, right. So, what is happening over here? You substitute x1 tilde. What are you going to get? What is x1 tilde? h1 star x by root c. So, what happens? h1 square by root c plus h2 square by root c into x. So, I put them together plus noise. Fine. What is c? Just calculated here, right? Is the square root of the term in the numerator. So, what you get? If you put c, right, the same term which is coming in the numerator, but with the square root. Correct, right? That is what is coming over here. So, you substitute, so one square root gets cancelled and you have this n. What is the SNR? What is the power of this divided by n naught? h1 square, h2 square, p by n naught. What is this? Exactly the same SNR what you saw for multiple receive antenna case. Okay? Same SNR as that of the multiple receive antenna case. Crucial that transmitter knows the channel. What is the difference? Why are you able to get this much of gain? Look at this, what is happening. Okay? Right? You are able to multiply it with h1 star. You should understand why it is happening, why it is same. Okay? You are able to cancel the phase of the channel, and the signals are getting added up in phase. When you did not know the channel, what was happening? They were simply h1 plus h2. If the channel are out of phase, the signal is cancelling each other, right? Okay. Now that you are pre-cancelling the phase at the transmitter, you are able to get the same SNR. So, the key point here is, it does not matter whether you have multiple transmit antenna or multiple receive antennas, provided receiver and transmitter have the channel information, you are going to get exactly the same capacity. This simple example. Okay. This scenario is crucial for downlink, because base station has multiple transmit antenna. So, what is that? What does user need to do? It needs to estimate this channel H1 and H2 and need to feed it back to the transmitter, right. So, that is why you saw that in our PUCCH chain, lot of bits need to go from receiver to the transmitter. That is why that payload was higher. Correct? Okay. So, that's the key reason. There should be some reason, right? The payload in PUCCH is higher. Okay. Because all this, see how crucial this information is. Without this information at the transmitter, all these multiple antennas at the transmitter, which are used in the downlink, are going to fail. Correct? Okay. In order for these to work, you need this information, and I gave you an example. So, that should give you a kick that how crucial this channel state information is. That is why you see so many pilot signals are defined, right. In order for this system to work, you need this kind of the channel information is so crucial. With a simple example, okay, right, we understand, and there is a motivation for us to understand different kind of pilot designs, how the channels are estimated. Okay. Hopefully, I have conveyed this that the receiver, it is easier for the receiver to estimate the channel. Transmitter does not know, because it is the receiver which is receiving the signal. Transmitter needs to be given this information, and how is it given? Receiver will estimate it and feed it back, as we saw, over PUCCH, right. Okay. When that MIMO is going to work. So, we will stop here, we will continue discussing this in the next class. Okay. Thank you.